torque is NIAB sine theta. In this case, remember that the angle theta is with the plane of the coil. And the question says the plane of the coil makes an angle of 30 degrees. So it is, that's a big difference. Sine 30, because the plane of the coil makes an angle of 30 degrees. So you get 0.48 Newton meter. Well, on number 2, this is how you get the equation. mv squared by r is equal to qvb sine theta, and theta is 90. It's always good to know how you get the equation. So most of you got the answer. R is mv by qb. Substitute the numbers for the mass and the charge of the electron. And it's 3.9 times 10 to the negative 3 meter. Here's number 3 for you, the same idea. Centripetal force is equal to magnetic force. Again, theta is 90 degrees. This time you have to find the mass. So rearrange to make mass the subject. Plug in the numbers. You get the answer. 6.4 times 10 to the negative 28 kilograms. Yeah, because remember, magnetic field is along the z-axis, so you only take the I and the j vectors, square them up and add them, you get the velocity, the perpendicular component. That's what I did. Okay, so you find that. You get it as 11.4 times 10 to the 6 meter per second. And then use mv squared by r as q v cross b, which is vb sine theta, right? And then I have to take the cross product of velocity with magnetic field, and that is how I take the cross product. IJK, velocity components 9, 7, and 5. That's 0, 0, 7 times, and I got this. And therefore, v cross b, again I have to square both the components and add them up, which I have not shown, but I have done it. Okay. I have squared this to find the magnitude of the velocity. Don't I have to do that? V cross b, so I got that. Then I have to put it back into this equation. That's the mass, velocity squared. Because I made the subject the radius, because I have to find the radius. Once I get the radius, I can put that radius back into this equation and find the time period. So 2 pi r by the perpendicular component. And I got this as the time period. Now, the distance moved forward is actually called the pitch. So it's v parallel times t. It's called the pitch of the helix. And my answer that I got is 3 centimeter. And the closest answer there is 2.6 centimeter. Okay, so. Yeah, so F is ILB sine theta. In this case, theta is 90 degrees, isn't it? Theta is 90, so F is just ILB. That's the diagram. And so that's the direction of the force. And the weight acts vertically down. Let's stop there for a moment and think. If the force is that way, weight is down, from that triangle, if you divide F by mg, what will you get? Remember, it's a whole lot of concentration that you need. F is along this direction, isn't it? So that's that side of the triangle, and mg is, hold on. MG is this side of the triangle. Are you with me? And you see the angle theta. So what's tan theta? Tan theta is opposite side by adjacent side, which would be certainly F divided by mg. That's the whole idea. So that couples with static equilibrium from semester 1. So it's both together. Therefore, F by mg is equal to tan theta, and tan theta is, now it's just math, ILB by mg, and you substitute the numbers given. Remember, mass is in grams, you got to convert it into kilograms. You get tan theta as 0.19 radians. Take the inverse to get 10.75 degrees as the answer. So number 6, B is mu naught I by the length of the solenoid. And the length of the solenoid is just the thickness times the number of turns. And then you know mu naught is 4 pi times 10 to the negative 7. You got to know that. And everything else is given. Of course, the number of turns will get cancelled and you end up with 251.32 times 10 to the negative 7, which is 2.5 times 10 to the negative 5 Tesla. Okay, here it is. Seventh one, maximum EMF is given by NBA omega. Check whether it's on your formula chart. No? All right, this is the second time it's coming up. Did you notice that? The first problem had NBA omega sine theta, so it's maximum EMF is the product of number of turns, magnetic field, area of the coil, and angular velocity. NBA omega. Easy to remember. NBA. Basketball Association. NBA. Omega. Just that. NBA omega. You'll never forget it. And you have to make the number of turns the subject. Everything else is given there. Well, of course, you have to find the area by length times width, isn't it? After changing them into meter. And remember that omega is 2 pi times f. That's why you have that 2 pi times linear frequency. Two pi times f. What is the applied EMF? 120 volt. And so when it picks up, you know that the greater the speed, the bigger the back EMF. So when it is operating at maximum speed, the back EMF is 105 volt. Now can you tell me this? What would be the current at that time? The applied EMF is 125, the back EMF is 105. So the voltage is only 15, right? And so 15 divided by 6 would give you, how much is that? 2.5? Come on. 2.5 amps would be the current through the motor at that time. That make sense? Okay, but when it begins operation, hold on, when it begins operation, what would be the current? What's the back EMF when it begins operation? Just when you switch it on, what's the back EMF? 0. So that means you have the entire 120 volts divided by 6, which is 20 ampere. That is dangerous. Because like I told you before, the insulation is microscopic, it's going to burn out now. If you let that 20 ampere flow even for a few seconds, you lost the motor. So what do you have to do for any motor? You need to have a switch which has a high resistance at the beginning. And as the motor picks up speed, that resistance should go from high to low. Did you get me on that? Why? So as to limit the current at the beginning. That's such a real application that I wanted to bring it. That's why I put that question in there. Any motor, at the beginning, you should limit the current to it. Well, when it picks up speed, within a few seconds, it's okay. back EMF is going to decrease the current through it. So now go back to this question. The question is, what is the starting current of the motor? And I've already given you the answer. What is the starting current? Come on. 20 amps. But I'm doing it both. I'm doing both. This would be the current, applied voltage minus back EMF. That would be the current when it's operating. That's not what is being asked here, okay? Just wanted to make it sure. That's the operating current, but at the start, the back EMF is 0. Therefore, I is just V by R. So 120 by 6, and you get 20 amps. Number 9, surely the ratio of the voltages is equal to the ratio of the turns. That's all you need. And put it there. Get 400 by 100 times 120. That is 480 volts. So number 10. Again, EM is NBA omega. A is 0.12 times 0.08 because you have to change it to meter. That's the area. And like I said, omega is 2 pi f, which is 2 pi times 1200 by 60 to get it into seconds. That's the omega. Now multiply all those. And 28.9 volt, just 29. Number 11. Force is mu naught by 2 pi. I1 times I2 divided by the distance between them. That's straightforward. And see, remember, that's the formula for force per unit length. Force on 1 meter. Hold on. If the question says, what's the force on 2 meters, you know you have to multiply this with 2. So remember that that's the force on 1 meter. So substitute, calculate 8 times 10 to the negative 5. If you look at the unit, you know it's Newton per meter. I had to put per meter there to show that that is the force on 1 meter. E is negative d phi by dt, and negative, just shows the direction. So, but here's the point. The magnetic flux is B times A. Do you remember that? And so d phi would be B dA. Because B is a constant. It's only the area that changes. And then plug it back into that equation. You would get negative B dA by dt. That's the formula. I didn't bring the n. To be perfect, actually, you should have an n there. But n in this case is how much? 1. Now, just make sure you understand that. To be perfect, it should be n. Yeah, it should be multiplied by the number of turns. But in this case, it's 1. So in this problem, if you had just found the area, change in area, you would get partial credit. No, what I was trying to say is, you did not do anything else, just found the change in area. You got at least 10, 20%, which is good. And the negative just shows the direction again. Magnetic field due to a straight conductor is V naught I by 2 pi. I put it as D. You can write it as R if that's how it's on the formula chart. Make the distance the subject. Put in the numbers. That's the Earth's magnetic field. That's 2 centimeters. Means it's working. All magnetic fields add up. Like you said, I took it like X, Y, the other way. That's why I took it right this way. Okay, that's what I said. Magnetic field due to C, you can see that, right? Due to A, B, C. And then I'm saying that the magnetic field due to A and B will be the same in magnitude, isn't it? A and B. A is here. I can't even draw now. A is here, B is here. They are at the same distance from that point. So A and B will be the same. And that will be mu naught I by 2 pi R for U. Anyway, 2 pi d. We used that before, so 4 pi times. Plug in the numbers, you get the magnetic field. (10⁻⁵ Tesla. Then find the magnetic field due to C, which is again the same formula, same current, but the distance is different. The distance will be square root 2 times 4 times 10⁻². So that I calculated as 0.7071 times 10⁻⁵. Then I have to find the total of it, of all the three, this way. Yeah, find the magnitude of that. And I get 2.1 times 10⁻⁵ Tesla, which is not in any of those answers. But I'll go with, that could be a printing error because you see the 10⁻⁶ minus 5 and all that. Got 2.1 times 10⁻⁵. And the answer is that's given here is 2.1 times 10⁻⁶.
So whenever we do these, just...
So P is I times V, 9 by 100, that's the current, times the voltage, so you get 0.81 watts.
But the real concept here is that you got to realize that because of DC current, we do not need to worry about the inductor, correct?
Exactly. And what I wrote down here we'll be using later on, but I just wrote it in an LCR. Power is given by IV cos phi. It's a good idea to write that formula down. We'll be using that again. We've not talked about it much in class, that's why I brought it up. In an LCR circuit, average power is given by IV times cos phi. Well, that's coming in one of the problems. We'll talk about that. In this question, focal length is -25. DO is what? 100. DI is to be found. And that's the formula. 1 by DO plus 1 by DI is 1 by F. Make 1 by DI the subject. So 1 by F minus 1 by DO. Be a little bit careful on these calculations. Negative shows that it's behind the mirror and that it's a virtual image. I had to draw the figure just for fun. 43, so the angle is 86 between the incident and the reflector. All right, 19. So because it's a concave mirror, focal length is given as 10 centimeter. You will take it as positive 10 and calculate again using the same formula. Don't think you need HO here, though, although I wrote it. DO is 8, F is 10, positive because it's concave mirror. Find DI. Make DI this 1 by DI the subject. Please don't forget to reverse it because what you're getting is 1 over DI. Okay, to get DI, you have to go 1 divided by -40. That means it's a virtual image, and magnification is negative DI by DO, isn't it? So put that back. There are 2 negatives now, so that's going to be 5 times magnified. So if it's negative, it's on the other side. It's a virtual image, and the magnification is 5. So the answer is C, 40 centimeter on the other side, and virtual, 5 times bigger. 20? Focal length 20. So that means it's concave, isn't it? Yeah. HO is 4. What is the position of the image? Same question, same process. That's like almost telling you that this is really important. 1 by di is 1 by f minus 1 by do. Means it's a real image, it's in front of the mirror. You're putting my voice on this. This is 22 that you did. XL by 2 pi L, and you get when you calculate, what did you get for 22? 796.17. Second, 22. I was 22. 23. IRMS is VRMS by Z. See, I did that first.
You would have to convert. It was-
First find Z.
Yeah, or vice versa. I think
120 by 0.4. 300 ohms is the impedance.
I know, or square it.
Then find the XL.
If you had one of the others, you just had to convert them. Yeah.
2 pi times F times 12.56. Isn't that what you got? 12.56, and XC was what? What did you get for XC? We'll see. Whether I made a mistake, because you can't. You're so many. 39.80 ohms. And then plug it back into that equation. Well, I took it as, I don't like to write the square root, so I wrote Z squared is equal to. Same thing. Make R squared the subject. This is a lovely and very important question, because it has all the concepts in it. Did you notice? You have to use XL, you have to use XC, you have to know IRMS is VRMS by Z, everything. 299.87 ohm is the answer. All right, 24 is equal to L di by dt. I didn't take the negative because that just shows the direction, and it will become a positive. And just check for any mistakes that I made. This is towards the end, and I'm really tired when I'm doing this. D by dt 0.5 cos 275t. When you differentiate, what do? You got to write the omega again, right? And differential of cos is? What's the differential of cos? Negative sign. So the two negatives become a positive. Okay, if there was a negative before. And so I got d by, hold on a second. But from there, I got d by dt, and then how do I go to d by dt maximum? Di by dt is what you see right here, isn't it? If that is di by dt, what is di by dt maximum? What's the only term that can change in that equation? Sine. And sine maximum is 1, isn't it?
Yeah.
So just take it as 1, and you will get d by dt max. So that's why I just multiplied 0.5 with 275 to get the maximum rate of current. Make any sense? So di by dt is something sine of an angle. So you want the maximum of di by dt. Surely the only thing that can change is sine and give it the maximum. So you get the left hand side to be maximum. So 137.5 ampere per second, and then put it back into this. E by this, and I just put the units there to just remind you that volt divided by ampere per second is going to become Henry. 3.64 is, that's why I was telling you. Don't worry about what's going on, I'm just sending it forward. 25, just read 30.
This is literally the same exact question we've already done in number 12.
Yeah, 25. I put the answers in another color, so
It's literally 12.
changing electric field to be magnetic field and sound
No, you're
wave.
wrong. So, isn't it person- Whole desk. I know, isn't it? Yeah. Wait, do I say it?
So
Last
that's
semester,
25 to 28,
always
to 29 rather.
all this thing. Yeah, being trained, you know. Yeah. And then all of that.
Average power dissipated, you have to find cos phi. Power factor. If you see a word called power factor, that is cos phi. Power factor, in that question it says the power factor is 0.05, so that's cos phi. And then maximum voltage is 8, it's understood. So, and you also know that, that's important again. The maximum current is maximum voltage divided by what? Minimum impedance. Maximum current is maximum voltage divided by minimum impedance. Are you listening? Because when the denominator becomes minimum, that the value becomes maximum. And what's the minimum value of impedance? Resistance. Why? Because at resonance, the other two become equal and opposite and cancel out. Is that making sense? Mm-hmm. So at resonance, remember the curve for resonance? Resonance curve goes up, and so at resonance is when the current is maximum, and that's because the impedance is minimum. And what's its value? Just the resistance in the circuit. Very important point. So I got the maximum current using that concept. And then PRMS or average power. PRMS means average power. That's the formula. IRMS times ERMS times cos phi. Now all you got to do is just plug it into that, 0.25, and you get 0.32. See, what I wanted you to know here is, just adding on to this, and that's just a couple more minutes. If you take a pure inductance, what is phi for a pure inductive circuit? What do you mean by phi? Phi is the phase difference between voltage and current. Okay, get back to your thoughts. For an inductance, what's the phase difference between voltage and current?
Voltage is ahead. By 90.
90 degrees. So your phase difference is 90. And what's cos 90?
1,
0. Now, that means an inductance does not consume power. Did you notice that? Because you have cos phi at the other end, and the same applies to a capacitance. Because, you know, again, the phase difference is 90 degrees. The difference is that one leads, the other lags. But take note of this. An inductance and a capacitance will not consume power, but a resistance will. So whenever possible in a circuit, we'll try to replace a resistance with an inductance or a capacitance. One good example is, if you take a regulator for a fan, a ceiling fan, or when you see those light dimmers, if you know what I'm talking about, dimming lights, those are inductances. It's not a resistance. What you're doing when you turn is, you're changing the inductance. Now, what's the advantage of using an inductance there? In olden times, we would use a resistance there. I don't know whether you've seen it, box-type regulators for fans, which would get really heated up. That's a resistance. Have you seen those? Old ones. That really is wastage of power. You know what you're doing? You're giving less power to the fan, but you're spending the remaining power here in a resistance. Now what happens? You have those tiny inductances. Have you seen those, like the tiny ones? Remember, an inductance and a capacitance will not consume power. And actually the current that flows through them is called a powerless current. It doesn't consume power.